Last time we did some cool stuff. It started out really beautiful. We learned that normal curvature, which I like to call cross-sectional curvature. Y'all remember the key point of that? Remember the key point, right? Was that you have some surface here, right? That we often draw it like this. You see the cross-section in the plane, right? And so you have a capital U here and then a little u here, right? And then you look at this cross-sectional plane here defined by capital U and little u, right? Now little u, there's a whole circle of possible little u. Now capital U, there's just really the one, or negative u also, right, pointing the other way. But so capital U, there's only one choice effectively. But little u, there's a circle of possibilities. And so what you get then is this normal curvature thing, which is, we call it little k of u, and that's because of capital K, which is the Gauss curvature, which is just simply, and it's the cross-sectional curvature, but we also realize it's u dot product the shape operator of u, all right? Now that uses the shape operator, which you remember is S of u equal to the negative covariant derivative in the excuse me. Well, I did use u there, okay. All right, so there we go. This is the book's notation. You ready? And the little u direction of capital U, right? Everything is u, but that's one's a capital, one's a lowercase, right? And then other key facts we learned last time were that the eigenvalues, I used lambda 1, lambda 2 last time, but now let's use k1, k2. Let's let k1 be the minimum value over all possible little u of the normal curvature, aka cross-sectional curvature. And then the maximum we'll call k2. By the way, the book may or may not follow that convention all the time. And I might not follow that convention all the time. That's just a convention, doesn't really matter, but 2 is bigger than 1, so I think k2 should be bigger than k1, just so I can remember what I'm talking about, right? It's just for convenience. You can do it the other way around if you really want. Doesn't matter, or just randomly. And then what was kind of cool about this then is that means that the shape operator then can be represented by a matrix, which is k1, k2, 0, 0, right? So here I'll say A equals, okay, here minus, and kind of board work is not perfect. Okay, so there's K1, K2 are eigenvalues of the shape operator. And then the eigendirection, that's with respect to some basis. What is the basis? Well, it's U1, U2, that's what the vectors that minimize the cross-sectional curvature. And what else? Oh yeah, the product, if you take the determinant of the shape operator, that's K1, K2, that's the Gauss curvature. Turns out that's an intrinsic curvature quantity, which we're going to prove today, I think. If we get to it. And then you can take the trace, and this is called the mean curvature. And we call it the trace. It's the trace of S, and that's K1 plus K2. In this course, it's called H is called the mean curvature, both in this course and outside this course. But what's interesting is in this course, it really is the mean of K1 and K2. So we define 2H to equal K1 plus K2. But after this course, every other paper you might find on the internet or whatever, it's not 2H equals this, it's just H equals that. And really it should be called the trace curvature instead of the mean curvature. But they still call it the mean curvature, even though it's not an average. Okay.
So in higher dimensions, we need to have 3H be K1 plus K2 plus K3.
In this class, we're only going to do two-dimensional surfaces. So, but I suppose if we would have to do that, wouldn't we, to be consistent? Yeah, it would be like 3H. But that's why in beyond this course, people don't do that. They're just like H. H is the trace of the shape operator. And it's just like trace and determinant, your main things. And so the word mean curvature, okay, it's like, okay, it's kind of anachronistic at this point. Should be trace curvature probably. Okay, so here's some things. By the way, at some point there's going to be a midterm. Does anybody remember when the midterm is?
20.
This month.
Yes.
Oh, it's coming up.
Yeah.
What's the date today?
12.
Okay, everybody a little scared? No, not should be scared. You should be anticipating, right? By the way, let's talk about that just for a second. You get to take a piece of paper, regular 8.5 by 11 piece of paper, inches, by the way. Some students show up with an 8.5 foot by 11 foot piece of paper one time to some exam because some professor didn't say 8.5 by 11 inches. They just said 8.5 by 11. Anyway, it's a good joke. But one piece of paper, front and back, but it has to be in your own handwriting. You can't type it, you can't print it, you can't photocopy it, you can't microfilm it. All right? It has to be in your own handwriting. And that is because, really, here's the funny thing. You guys know what I'm talking about? I mean, isn't it nice to me to let you have a review sheet that you can take in? Some people call it a cheat sheet, but it's not cheating, right? It's a review sheet. And you can take it with you on the exam. You guys are aware of the fact you can basically write an infinite amount of information on one piece of paper, right? I mean, I might as well have made it 8 feet by 11 feet, right? I might as well.
Right on both sides.
Both sides, yeah. Okay? So, because you can write small and everything, but on the other hand, it's not quite infinite. I actually like it because you have to figure out what do I put on it. Okay? So my suggestion is you have a rough copy, like you can have a 5-page review sheet right now. You should write all this stuff down, right? What are the key concepts? And then at the very end, 2 or 3 days before the exam, you decide, okay, what do I actually want to put on my review sheet? And then the funny thing is, by the time you go through the process of deciding what to put on there, you've learned it. You probably won't even look at your review sheet. That's why I like review sheets so much. Maybe it's just there as a security blanket, right? But it gets your brain in the right frame of mind, which is, this class is not about memorizing this. It's about using it and understanding it to solve problems, right? So don't ever think you have to memorize it. You can put it on your review sheet. And then we had some other things we did last time, which is we had these E, F, and G's, right? We have this, just doing a little mini review here. We have a coordinate chart, right? We always call the coordinate chart the U, V axis. And then we can map this into our surface, right? There you go, there's your coordinate chart. And at any given point, like maybe this point here maps to this point here. And then you can think about going in the U direction at unit speed or the V direction at unit speed. And that maps to 2 vectors over here, XU and XV. And XU and XV are just the partial derivatives of this mapping here, which we call X of U comma V. Okay, and this is all in 3 dimensions over here. X, Y, and Z. And so this is, of course, equal to, X of U, V, comma, Y, comma, Z of U, V. So it's 3 functions of U and V. And by the way, let me just point something out. We have a mapping, this X is mapping, the UV plane into R3, right? But you also have this X star, and that's mapping, if I take the point P here, and we go over here to, we call this P, right? This is P, P is equal to X of U comma V. So what should we call this? We call this point Q, okay? So if we take the tangent plane at Q of this R2 here, it gets mapped to the tangent plane over here at the point P, okay? And I haven't mentioned this before, but what is that X star, right? This is mapping points. This point Q goes to P, right? That's what X does. What does X star do? Well, it maps tangent vectors to tangent vectors. And what is a tangent vector? Well, it's a velocity vector, right? It's the velocity of a curve, right? And so if I have a curve, so what does this mean? Well, suppose I have a curve over here whose velocity vector is this unit vector in the U direction, which, by the way, I'm going to call partial U, by the way. I think that's a good name. And this one here we'll call partial V. And partial U, that's coordinates 1, 0, and partial V has coordinates 0, 1. Then the point is, if this is the velocity vector of this curve, then you use X to map the curve over here. Okay? And then whatever the velocity vector of the image curve is, that's what this, so yeah, so x star of partial u is equal to xu as an example, right? And more generally, this x star of some vector v is equal to w if v, when v is the velocity of the uv curve, and w is the velocity of the image curve. Okay, so this is defined in the book as well, but let's focus on the idea here. Okay, I want to point out that there's something that this is, if this map didn't exist, this x lower star thing didn't exist, we would have to define it, right? Because it's something very, very natural here, right? You have a mapping x, which maps points to points, which means it also maps a curve over here, could we get mapped to a curve over there, right? Which means that you have a one-to-one identification of velocity vectors over here with velocity vectors over here. The velocity vector of this curve, by definition, gets mapped to whatever the velocity vector of the image curve is at the same point, right? So we would have to define it. So there's something extremely natural about that. Okay, so in this case, partial u, which is go in the u direction over here. By the way, it's a reasonable name for that vector, isn't it? Right? Because what does partial u mean? Right? It means. By the way, we could just notation here. I don't want to clutter the board up too much. I'll just erase it. But partial u is also equal to d du. Okay, these are just the same symbol. Okay, this one's saving a little chalk. Right. We're taking the partial derivative with respect to u. What does it mean? It says hold v fixed and increase u. Okay, so if we do increase u at unit speed, how would we call that partial u? Isn't that a reasonable name?
I'm confused. So this looks like this looks like that was like an operator, right? Like you take the partial of something. So how are you entering?
This is an operator too.
Right. So how are you entering that into like?
Well, because this is you take a directional derivative. I mean, if you want to think of this as a vector, for example, the directional derivative of this vector is that operator.
Okay.
Right, what are vectors? In fact, let me throw a new concept on you that you probably haven't thought of before. You previously have always thought of vectors as ordered pairs of numbers and things like that. Okay, throw that out the window. A vector fundamentally is really two ways to think of it. Number one is the velocity vector of a curve. Okay. And number two, it's an operator. It's a directional derivative. Like if you have a vector, I could take the directional derivative of a function in that direction, right? And really, these last two ways are the right way to think of vectors, because what it really is, if you give me a vector, it's the velocity vector of a curve, and what can I do? Well, I can take the derivative of a function along that curve, can't I? Okay, so let's think of, so really vectors are our first order operators. It's really kind of what they are, and they're also, and the way I understand it, they're first order operators is I can take derivatives of functions along the curves that they're the velocity vectors of. Okay, so that's the intrinsic way of thinking of what a vector is. And then the whole thing about a vector is it's like a number, comma, a number, comma, a number. That's just a way of representing it if you happen to be in three-dimensional space or something like that, right? But let's have that more abstract definition. Okay, and so the point is, if I think of the curve, see how I drew an interesting curve here so that you could see what the image was over here at some curve. It's curve to curve, right? But actually the most boring curve here is a straight line going straight across where v is fixed, right? Going with speed 1 directly across there. Then by definition, the velocity vector of that curve is partial u. And then the image is going to be some curvy curve over here, but it's going in the direction of xu, which by definition is the direction that x is going when you hold v fixed and increase u. And so therefore we have that statement. Also true for partial v. Okay. And so just to summarize what we did last time is we had these quantities. We defined E, F, and G. This is xu dot xu. Now that dot product there is being done in the R3. Okay? Xu and xv are three-dimensional vectors in xyz space. So that's, the three-dimensional dot product. You also can do xv dot xv, and then we can do the cross term, xu dot product xv. And that's what we call EF and G. We also can define L, M, and N. Which, by the way, you're going to get really familiar with these letters. When someone says what L is, I mean, it's just you're going to put all this on your review sheet. I'm basically helping you make your review sheet here. I mean, like 2/3 of what I'm writing down is probably make it to your review sheet. You can do the shaper operator of XU, and then dot product it with XU. You can do the shaper operator of XU, and then dot product it with XV. And by symmetry of the shape operator, this is the same thing as the shape operator of XV dot XU, right? So the shape operator is symmetric, which you should be able to prove. Expect that to be on the exam. And then the shape operator of XV dot XV we can put here. So this is really every combination. And that's L, M, and N. And then what we learned last time is that there's this thing that we can actually, through some rather messy identities, including Lagrange identity and so forth, right? We get this messy formula for K, which I don't have memorized. You kind of accidentally sort of could probably remember it, but I mostly look these things up every time. Okay, so the Gauss curvature, which is the determinant of the shape operator, can be expressed. This is the easiest way to compute it, right? And then we also have H, a formula for H as well. And it's, let's see, what is it? GL plus EN minus 2FM, I think. By the way, the fact that these formulas exist is interesting. And you will, and of course, I think are you already using these formulas in your homework, or you will, for even the one you did last time? Yeah. Okay. So you're going to want to, so you see the usefulness of them, right? But I don't go around memorizing stuff like this. Why would I do that? It's in the book. Life is an open book exam. But I do understand, you want to understand where these formulas come from, be able to derive them, for example. But today we're going to find out there's a formula for K, and it's just a function of the EF and Gs. Now that's really quite surprising, okay? And I wrote the formula down last time, and I'll write it again down later today, okay? But what we're going to do is derive a formula for K that just depends on EF and G. And that's really quite remarkable because on the surface it looks like it depends on L, M, and N. And well, of course it does, right? Because it's a term of the shape operator. The shape operator is extrinsic geometry. Right? L, M, and N essentially represent the shape operator. They're the coefficients of the shape operator effectively. If it has all the information in here. And I think I'm going to skip these examples. You guys have already been doing examples in your homework, but what's missing from the board here is, someone gives you some surface, x of uv. So in other words, what is the surface? That's the surface. Give me a parameterization of a surface. Sometimes that might be your starting point. Now sometimes someone might say, no, it's a sphere. It's x squared plus y squared plus z squared equals r squared. Then the first thing you have to do is parameterize the surface, find some x of uv that covers it, right? And then you plug in and you figure out your XU and your XV, and that allows you to get EF and G. Now to get the shape operator, we need this capital U, right? Now remember what capital U is. Capital U is equal to XU cross product XV, and then divided by its own, that length, right? So that you get something with length 1. So that's you got to do that step, right? And then once you have capital U, then you can compute the shape operator in various directions, blah, blah, plug it in, right? And there's a key step that y'all are going to be doing a lot, which is, there were some other formulas in the book, right? For example, this equaled, can anyone remind me what this equals? It equals capital U dot product XUU, is that right?
Yeah.
and this equal capital U dot product X U VV, right? And this one up here is equal to capital U dot product. This one has space, right? Okay. Capital U dot product X U V, right? And that was how we proved the symmetry of the shape operator, right? So the point is, in fact, these formulas are probably the easiest way to compute L, M, and N, right? So you compute the capital U, you compute XU, you already have XU and XV, but then you take the second derivatives of X, and you can compute your L, M, and N's. And so you can do this for the surface of revolution. It's in the book, sphere, torus, compute all these different quantities. It's tons of fun. Right? And there are examples in the book, and I'll refer you to those examples. But what I want to get to today is this fact that K is a function of E, F, and G. And Gauss is the first to realize this. And so he's the first to realize that there's this thing called intrinsic curvature. By the way, there is no intrinsic curvature of a one-dimensional surface. Like one-dimensional surface would be like a curve. Think of a curve like a path, right, in three-dimensional space. There is no intrinsic curvature. It's just how far along the curve are you, right? There's just distance from the starting point. That's it. Like the real number line, that's it. There is no, you can curve it, but there is, when you curve it in three-dimensional space, yeah, there's extrinsic curvature. It's curving the three-dimensional space. But if I say, think of a curve in three-dimensional space, and then I say, now think of that curve without the three-dimensional space. And this Zen exercise, right? The point is there is no curvature to that curve anymore. Its curvature was purely how it curved in the three-dimensional space. You get rid of the three-dimensional space, no curvature left. It's just, how do you go? How far do you go forward? There's no way to do an experiment. Like if you're an ant on that one-dimensional curve, right? If it's truly one-dimensional, right? You can go forward, you can go backwards. There's no experiment you can do to detect anything weird. But if you're an ant on a sphere, we know that if you try to make a square, you don't come back to where you started. Right? That ant doesn't need to know about three-dimensional space to detect, hey, there's something weird going on here. Right? And that's the experiment you can do to detect curvature. So in dimensions 2 and higher, you get this thing called intrinsic curvature. And so now we're going to get a little bit, we're going to do some calculus. You guys, is that okay with you guys? And it's going to get a little messy.
Are we allowed to say no?
It's mostly a rhetorical question, yeah. And I just, before we get into all the technical stuff, we just say, I find it intimidating too. I remember. It's like you just have to build up a tolerance. And I'm going to go fast, but when you're studying and understanding it the first time, you need to go slow. That's the trick here. And basically it starts like this. Newton, I mean, it's not Newton, might as well have been, but it was Gauss. That's what Newton wished he could have. So it starts with Gauss thinking, okay, what is x of u equal to? Good question, right? I mean, x to u is so important. It's a tangent vector. Xv is a tangent vector, right? Okay, one derivative of x, kind of important. How about two derivatives of x? Well, it's a vector, right? And what we're going to do is, for the rest of the computations here today, we're going to assume f equals 0. Okay? Now, what is f? F was xu dot xv. So in other words, we're going to assume that xu is perpendicular to xv. That's what we're going to assume, okay? We're just going to, it's an assumption, okay? Now, everything we're going to do today, you don't have to do that. If you just love punishing yourself, you can do all the calculations we're about to do where f doesn't equal 0. It's just going to make it more complicated, okay? And you get formulas. And the book has the formulas in there somewhere, what happens. I personally don't want to think about it. Now, why are we going to assume f equals 0? Well, guess what? We're just saying, look, would you please just don't, okay, you can choose almost any coordinate chart you want, just don't be completely stupid about it, right? We want xu dot xv to equal 0. Now, it turns out that it's still an infinite number of coordinate charts that have f equal to 0 for any surface. So it just makes the calculations a lot easier. So let's do that first. And then at the end, we'll just say, by the way, people have verified you don't actually need f equal to 0, it just makes the formulas more complicated. Okay, so xuu is a vector, which means, by the way, what does this all mean? Maybe I'm going to be a little more precise here. Okay. Assume, let me just write it. I'm not going to prove. Assume f equals 0. This implies xu is perpendicular to xv, which implies that if we have a perpendicular frame, or perpendicular vectors, xu, xv, and capital U. Do you guys agree that they're all perpendicular? See, xu and xv are tangent vectors, so they're perpendicular to capital U, but now I'm assuming xu is perpendicular to xv, so that's practically an orthonormal frame. Okay? But it's not quite, because xu and xv don't have to have length 1. I just said they're perpendicular, right? So what is a perpendicular frame? So we get, I think the word frame already means orthonormal. Is that right? Or does it? Maybe someone could look up what the definition of frame means, but I'll go ahead and say orthonormal frame. Orthonormal frame. We actually get an orthonormal frame. What it is going to be, it's going to be xu divided by its length, right? But what's the length of xu? Well, xu dot xu is e, right? And that's length of xu squared is e, right? And so, what's that?
It doesn't have to go.
Oh, okay, so a frame just means what? Just
It's
linearly independent?
It's a generalization of a basis.
What's the difference between a basis and a frame?
So it's a generalization to sets that may be linearly dependent. I don't know.
Okay, I refer you to the internet. Okay. Vocabulary. I should know the difference between a set of basis vectors and a frame. Maybe it's practically synonymous. Anyway, so the square root of e is the length of EU. So if I just divide by the square root of e, now this has length 1. And then if I divide this by the square root of g, that has length 1. And then this already had length 1. So that actually is an orthonormal frame. How convenient. Now if f didn't equal 0, I could come up with some formula to give me an orthonormal frame also. But it'd just be more of a hassle. And so when I'm computing this xu u, I know it's going to be linear combinations of these three vectors because this is a three-dimensional vector. And so this is going to be so much xu plus so much xv plus so many u. Okay, I'm leaving caps there because we'll just go ahead and fill it in.
It says frames. Frames don't have to be minimal spanning sets, but bases do. I don't know why. Why you want.
So you could have 4 vectors and still be a frame.
Okay.
Ah, hey, I actually learned that for the first time today. You guys, all right. So okay, but why would you want a 4th vector? I mean, we'll use the minimum number, right? Okay. Just vocabulary. Vocabulary is something I've never been that interested in. Okay. But of course, it's important to be able to communicate. All right. Now, how do we do this? Let's call this unknown here. By the way, in the book, okay, I'm going to just write down just for a second. They call this gamma. Let me make sure I get it right. Gamma u, I think. All right. You all see the logic of this? And this right here is gamma. I'm going to erase it, don't worry. UUV. Right now, here's the logic. See this UU here? It's there and it's there. And then the coefficient in front of XU, you put a U there, and the coefficient of V, you put a V there. So actually, there's logic to the notation. Okay. And the book explores that, okay? And so, you know, absorb it, try to figure out what logical notation is and so forth. Gets a little confusing, it looks messy, doesn't it? It's like, what are you talking about here, right? Let's just solve for these things, okay? How about this? I'll be a little friendlier. And then the question was, well, what is that term? What should that be called?
L.
It turns out it's L. Why is it L?
If you dot both sides by U, then only the one on the right, only the U part of the frame.
Very good, because these are perpendicular vectors. If I dot product both sides by U, then I get something times 1, right? And here, actually, U dot U, that's L, right? So this coefficient has to be L. Do you all see that? Dot product both sides by capital U, and you get 0, 0, whatever this coefficient is times 1 is equal to XU dot XU, which is, we see, L. Okay, so that must be L. Okay. Now, how can we find this coefficient? Same idea. Dot product with XU on both sides. You're going to get 0 here because of the perpendicular, right? XU dot U is 0. XU dot XV is 0. XU dot, now what is XUU dot XU? Well, okay, let's be careful here. Let's call this A and we'll call that B. In the book they have it more complicated, the gamma U you use, okay? But if we dot product both sides by XU, you get XUU dot XU is equal to A times XU dot XU, and then plus 0 and plus 0, because XU dot XV is 0 by assumption, and then U dot XU is 0 because they're perpendicular. This is all in the book, by the way, so I would pay attention more than I would take notes. We're trying to decide which to do. And then you're like, oh, what's this? And you come over here, XUU dot XU. I don't see it. Don't see it, do I? But then you're like, well, wait a second, this is almost that. XU dot XU, that's almost XUU dot U. And then you stare at that for a little bit longer and say, wait a second, what if I take the U derivative of this? Isn't that, oh, that's going to be 2 XUU dot XU, isn't it? Right, if I take the U derivative of this, I gotta use the product rule. I get XUU dot XU plus XU dot XUU, right? And so you're like, oh, wait a second, so the U derivative, so actually this is equal to just 1/2 the U derivative of E. Right, because I get a 2 coming out, right? So I gotta divide by 2, but otherwise that's where XUU dot XU is. And now how about this XU, now that's E right there, right? So you get the left-hand side is 1/2 this, and this is equal to A dot E, right? Everybody follow? Doing some calculus here? And so then you're, oh, okay. A is equal to EU divided by 2E. Okay. All right, cool. Let's compute V. Well, let's dot product both sides by XV, right? And then what we get is XUU dot XV equals 0 plus B times XV dot XV, right? Plus 0. Everybody follow along? I just took the top equation here and dot product it with XV on both sides. And then, you guys mind if I just erase this and put a G right there? XV dot XV, we see that's the definition of G, isn't it? Yeah, okay. You mind? We'll be able to check it later, right? But that's G. And then we look at the XUU dot XV, and we're like, okay, well, where's my XUU dot XV over here? I figure it's got something to do with f, right? I mean, that's the closest thing. So let's go over here and do something with f, right? So we figure, okay, look, f by definition is xu dot xv, right? And then we want to get to an xuu dot xv, so how about we take a u derivative, right? And so then what we find is that f sub u, by the way, remember we were choosing f, we assumed f was 0, didn't we? We did, didn't we? So now let's take the, but still, nevertheless, that is xu dot xv, right? So let's go ahead and take the u derivative of both sides. So then you get 0 is equal to xuu dot xv. That's the term we wanted. But there's another term from the product rule, which is xu dot product xuv. Are you ready? Fair enough? This is the term we wanted. But now we got to figure out what this is. So we come over here to the x. Which term here kind of reminds us of that? Well, there's kind of two terms. The top two are both in contention, right? Rule of thumb. We used this identity just now. If I use it again, I'm probably going to just undo what I just did. That's what you mean. Go ahead, do it. Play around and see what happens. So just go back to where you started, right? So let's use this equation because I know I'll be doing something different at least, right? And so we have E is xuu, right? And then you're like, oh, wait a second, if E is equal to xu dot xu, that's what I like to say. Then if I take the v derivative, EV, right, is equal to 2 xuv dot xu actually, right? Because I get the same term twice. Take a v derivative again, xuv dot xu, and the second one is xu dot xuv, right? So I got the term twice. Well, that's this mystery term here, right? But except for a factor of 2. So then what we get then, if I take this to the other side, well, I get xuu dot xv is equal to the negative of this, which is equal to, I think it's negative EV over 2. Is that right? Is that right? Okay. So what's B? So in other words, this right here, xuu dot xv, this is negative E over 2, right? Negative EV over 2, sorry. And so if I want to solve for B, I got to divide through by G. So I get negative EV over 2G. Can I say what happened there? Okay, sometimes I put these problems on the test. Sometimes. I've done it before. The second one is harder. You see how there's 2 steps? We had to take f. But this was what was tricky. We assumed f was 0, but we still took the f equation. We used the fact that f was 0, and then we took the the u derivative of both sides. Right, and then and that gave us this, and that said that the thing we're looking for is equal to this. But this was we used the trick from the first step, right? And then we were able to solve. Yes.
So the goal of this is to find x or k as a function of only intrinsic geometry.
Ultimately, yes. Although at this point it would be completely unclear how we're going to do this.
Okay.
There's no way for you to guess how we're going to do this. So now I'm going to use the eraser method, if you guys don't mind. We solve for A. A was equal to this. So instead of A here, I can put it in E sub u over 2. E sub u over 2E. Right? And instead of this B here, I can see that we solve for B, and we got a negative E sub V over 2G. And there you go. We now have a formula for xuu in terms of things we know, E, F's, and G's, and xu, xv's, and u's, and l's, and m's, and n's, and stuff like that, right? You guys know how to compute all these things. Any questions about this? I'm now going to erase everything here. So if you have a question about any of these, it's in the book. By the way, before I erase it, suppose f wasn't 0. we could have done all this. It's just that if f were in 0, I'd have an f sub u here, right? And I'd have to keep track of the f sub u and blah, blah, blah. It'd just be annoying, all right? And also, what else would be annoying is this thing here. They wouldn't be perpendicular. So I wouldn't be able to say that when I'm doing here, I'd have more linear algebra to do. I have to solve for the coefficients and stuff, right? It's just more annoying, right? Invert a matrix at some point. Right, 2 equations, 2 unknowns, as opposed to just, oh, they're perpendicular, so it's way simpler, right? So, and I would never ask you to compute this when f is not 0 on the exam. That would take way too long. It could be a homework question, though, but I don't think it is. But it could be. If you just really want to punish people. I think it's more, you know, take a look at the formula in the book and someone else did that, and you can kind of look at it and see how painful it was. Okay, so here's the point. XU equals that. And you see how we compute that. And you can do formulas also for XUV. If you do exactly the same stuff, the formula you get for XUV is, I'm just copying this out of the book, by the way. And no one in their right mind would memorize this stuff. Can we agree? So we can get all the second derivatives, all the second partial derivatives of x in here. Same basic principle. The same tricks. Exactly the same tricks. You guys believe me? The same tricks. And that's what you get. And then we have 2 more formulas we want to put on our list. By the way, these formulas should be on your review sheet. Now you might say, why would I ask you to put these on your review sheet? Well, peace of mind. Like, I mean, what if you need them and on the exam, right? Peace of mind. I'm not going to deliberately write a problem where, you know, what is XV? You know, like, you know, or excuse me, what is XUV or something like that. That's not gonna, that wouldn't be a problem, but yeah, why not put them on your review sheet? By the way, we also have formulas for the first derivative of u and the first derivative of v. And these are quite straightforward. One thing is, there's this trick we use, like I said, 17 times, right? 1 equals capital U dot capital U, right? So if we take the u partial derivative, right? Then we get 0. Derivative of 1 is always 0. And over here we get 2u dot u, right? So the point is, this any derivative of u in any direction, that's perpendicular to capital U, right? Because it's a unit vector. It's the same trick we use 17 all the time. So in other words, the coefficient here is 0. Okay, so yeah, it's going to be, when you express it as a linear combination of xu, xv, and capital U, but it's perpendicular to u, so this last coefficient there will be 0. Right? Let me go ahead, dot product with u on both sides. We see that that's 0. Okay, and then what's this coefficient right here? We take u and dot product it with xu. And so how do you find this? Well, you take the dot product of xu on both sides. And remember, the same trick. Let's just see if we can do this in our heads. You guys want to go do this in your heads? I do this with my kids all the time, by the way. I will do math, and I will say, let's just do this in our heads. Now, you might say, why shouldn't I write everything out? Well, I write most things out. But it's good to practice in our heads every once in a while. And let me tell you why. You should practice this. because this allows you to do math whenever you want. Everyone has a little scratch pad in their head. Some people, it's the size of a little yellow Post-it note, right? Some people, it's half that size. Some people, it's twice that size. And if you get really good at it, it might be the size of a piece of paper, right? Imagine if you could have notes in your head the size of a piece of paper and you just doing math, like just like this paper all the time, like in your head. Wouldn't that be awesome? Well, start practicing, right? I mean, because then you can do math in the shower. You can do it while you can dream it. You can while you're walking to class, you're reviewing, you're doing calculations, right? Wouldn't that be just amazing? Okay, yeah, you can do it. It's just a matter of practice, right? In fact, you might already be doing it, am I right? A little bit? But am I also right that you wish your Post-it note was a little bit bigger? It's like, oh gosh, it's like, and that is the problem we all struggle with, right? So let's just do this problem in our head, just for fun, right? Take the dot product with xu on both sides. We're trying to figure out what goes here, okay? When you take the dot product with xu on both sides, we're going to get a 0 over here, because xu dot xv is 0, right? xu dot xu, that's going to give me an e by definition, right? xu dot xu is e. And then this u sub u, what is u sub u? That's the definition, that's the same thing as the covariant derivative of capital U in the xu direction, right? And then, so that's, in other words, that's a shape operator, except for the minus sign, right? That's the shape operator of xu. And when you dot product with xu, you get the shape operator of xu dot xu, right here, right? And so what you actually get then is minus L here. So you get a minus L here, you get an E here, and so this must be minus L over E. Okay? It's in the book. You can do the same thing with taking the dot product of xv over here. Take that dot product of xv on both sides, you get a 0 here. Shape operator of xu dot xv, that's right here, that's our m, so that's going to be a minus m because the shape operator has that minus sign in it, all right? So we're going to get a minus m, but we took the dot product over here as minus m when we take the dot product with xv. But this is going to give me an xv dot xv, which is g, so we get minus m over g. I may do the same trick down here, and this is minus m over e. Minus n over g, apparently. We're having fun yet? Calculus. Linear algebra, dot products. Actually, it's pretty straightforward, isn't it? It's just messy. Like I said, we're going faster than study this for an hour or two, right? Go through it, make sure you understand. Yes?
Question at the very beginning of the process.
Uh-huh.
When we dot product the first equation, both sides by xu, we had xu dot xu on the left-hand side. The first equation
Yeah.
of the series. The
Oh, up
very
here.
first.
Yeah, okay. Yep.
We dot product xu
Yeah.
dot xu.
Uh-huh.
Then applying that logic over there,
Uh-huh.
shouldn't that be 0? The u dot u is 1, and then you take the derivative of both sides.
Are you talking about this equation?
No, the middle board.
Yes.
Yes. So xuu is the u derivative of xu if we multiply both sides by xu.
Oh, xu it doesn't have constant length. So we can't do this. Like xu dot xu is not 1.
Xu dot. Oh, cool. That makes sense. Thank you.
Very good. Okay, notation, right? That's what got you there, I think, right?
Okay.
U dot u is 1, but xu dot xu is a function of u and v. It's called e. It's
Okay.
actually could be it's some complicated function.
Okay.
Good question. Good question. Yeah. Other questions before we move on? Let me tell you the difference between amateurs and pros when it comes to mathematics. Tolerance for pain. Because most people would compute these formulas and say, hey, look what I did. They put a box around it and say, I'm done. And then they would publish a paper and say, look how smart I am, okay? And then that would be the end of it. Okay, what else should I do? What should I do next? Right? But not Gauss. Gauss was like, oh, well, the second derivative is interesting. What about the third derivative? Let's just keep going. And I guarantee you he computed the fourth derivative, and I wouldn't even doubt if he went to the fifth derivative, right? But it turns out you don't get anything new in the fourth and fifth derivative. But you do get something really cool when you go to the third derivative. Okay? By the way, Gauss also computed like the first gazillion prime numbers. What a nerd. And he's sitting there, I mean, seriously, gazillions. I don't remember. Can anyone look up how many prime numbers Gauss computed by hand? This is before computers, right? We're talking 1800s, right? He's sitting there computing a lot of prime numbers. And then he said, oh, I noticed a pattern. The number of prime numbers, or he figured out that the probability a number should be prime is roughly 1 over the natural log of the number, which actually is true. I mean, that's called the prime number theorem, effectively, when you put it into precise terms. The probability a number of prime is roughly 1 over the natural log of the number. Isn't that amazing? You figured it out yet? Okay, so tolerance for pain. So, there's a lot. I mean, I remember, I think he was commenting on, I don't understand. I heard him commenting on the number of primes less than like 1 million and stuff. But I was like, he couldn't possibly have done that, could he have? I just don't know. I just don't want to put past him.
Oh, at most 1,000 digits.
What's that?
His theory was at most 1,000 digits.
At most 1,000 digits, what, of how many, to test if it's prime or not?
Yes.
Okay.
So,
Whatever. I mean, it sounds like something crazy.
okay.
But did he really compute all the primes up? He couldn't have done it up to 1 million. That's ridiculous,
This
right?
is also in French, so.
Okay. You know what it was? I think, okay. This is what he was doing. He wasn't doing all the primes up to 1 million, but he was computing the density of primes. So he might go from 1 million plus a million plus 1,000. He might do like little gaps there and so forth. But anyway, enough to where he started noticing what the density of the primes was. That no doubt is what he did.
Yeah, you definitely can get up to 1,000.
Okay, so you can do the same thing and compute. Hey, what's x u v, for example, equal to? All right, third derivative. You also can say, hey, how about x u v u?
Say.
And how many different possibilities are there? Well, I'll let you count them up. It gets, I mean, we got 3 here. You can take u derivatives and v derivatives, all right? But some of them are duplicate, right? Because partial derivatives commute. But in fact, then you realize, oh, wait a second, these in fact are the same, aren't they? These are the same, right? Because partial derivatives commute x u u v is the same thing as x u v u, right? But actually, we can compute them 2 different ways, though, because, see, we can think of this as x u u. So these are equal on the one hand, okay? On the other hand, this is x u u and take the v derivative. This is x u v and take the u derivative. Well, what's x u u take the v derivative? Well, there's x u u. Now take the v derivative. And what you see is you get an x u v there, but I have a formula for x u v. You get an x v v there. Oh, but I have a formula for x v v. You get a u u there, but I have a formula for u u. Pretty cool? Yes?
Does the commutation of partials depend on like xu and xv being like orthogonal?
No. No, this is just a multivariable calculus fact that partial derivatives commute. It's just, in fact, just to really, if you let's take x cubed times y to the 7th, right? Let's take the x derivative first, right? d dx. I get 3x squared y to the 7th. Now let's take up the y derivative, right? I get 3x squared times 7y to the 6th, right? But imagine I did it the other way around. Take the y derivative first, then the x derivative. I'd also get this, right?
Yeah, but x and y are orthogonal. Like I was asking, is it necessarily true if they're not?
What do you mean they're orthogonal?
X hat and y hat are orthogonal.
So there is partial derivatives only refer to coordinate derivatives. So in other words, I think what you're pointing out is partial derivatives commute for coordinates, right?
Sure.
All right,
yeah.
and x and y are coordinates, so they commute. But u and v are coordinates as well, and so they commute. So it has nothing to do with whether it's not xu and xv being orthogonal, it's u and v are coordinates,
Okay.
x and y are coordinates.
Yeah.
Okay, but good question. Because like, so in other words, let me tell you what doesn't commute. Directional derivatives with vector fields. That doesn't commute. Only coordinate partial derivatives commute. You guys get what I'm saying? So if you're taking, we're not taking, yeah. So differentiation with vector fields doesn't necessarily commute. Like if I have a vector field and I apply it to a function and then apply another vector field to it, right? That doesn't necessarily commute. And you might wonder, well, when do they commute? Exactly when they're the vector fields corresponding to some coordinates. So coordinate partial derivatives commute.
The covariant derivative commutes as well. Yeah. Then we have a homework problem showing that second covariant derivative. It doesn't matter what order you do it.
As long as it's a coordinate partial derivative, yes. So I don't remember the homework problem you're referring to, but coordinate partial derivatives commute. Everything else, all bets are off. Yes?
So what you're saying is when the directional derivatives are just themselves like partial u or partial v?
Correct.
Okay.
So yeah, so actually xu and xv are just the same thing as partial derivatives with respect to u and partial with respect to v, and so their directional derivatives will commute. But that's the only time actually it turns out that where you can say they will always commute is when they are vector fields. So we're getting a little complicated. We're going off on a tangent, right? Partial derivatives of coordinates, whether it be functions of x and y or functions of u and v, they always commute. That's the main thing. But I'm not saying all derivatives of all kinds. Like directional derivatives actually in general don't commute. If I had just two random vector fields or something. Okay, so we know these two things are equal. And we also have this clever way of figuring out what their expressions are. Let's go ahead and do it. And so the point is we get so many xu plus so many xv plus so many capital U, right? And this will be so many xu plus so many xv plus so many u. And we have a way of computing these things. But it turns out, and of course Gauss compute all these things. But let's just compute the one where I have the big gap here, okay? Oh, well, I have enough space here, actually. Okay, let's do xu, u, and take the v partial derivative. We're just going to keep track of these, okay? Now, here's the key point, is that this equals that. Whatever expression ends up here, I mean, this equals that, and that equals that. Why? Because these two vectors are equal. Partial derivatives commute. So we're going to get an identity out of this. Turns out this equaling that doesn't, and this equaling that. It turns out there's only one identity that comes out they're all the same identity. I mean, you wonder why do we choose this? Because it turns out you get one new identity that comes out of all of them, right? And we'll find it in this spot here already, so we don't need to compute everything else as it turns out. But of course, Gauss did everything. We need this for the first time. Okay, so what's xu, then take the v partial derivative. Okay, well here's xu. Take the v partial derivative. Well, you get eu over 2e. I'm not sure. I might have to erase this. Let's see. Times, we're taking the v partial derivative, so I get xuv. Xuv is this. Now, how many xv do I get? I get gu over 2g. Okay, there we go. So xu, take the v derivative. Okay. Guys, remember the product rule, right? Taking the v derivative of this. xu, take the v partial derivative. Now, I took the derivative of this term, the derivative of this term is irrelevant because I get xu, they all end up over here, right? So I actually do the product rule on all this. So derivative of this times xu ends up over here. Then I do this times the v partial root of this, I get xu v, that has a v term, so it shows up here, okay? Come over here, take the v partial derivative. Well, I get something times xv. This is, I'm collecting my xv term, so then I'll have a minus ev over 2g. Take the v partial derivative, xv, and then minus ev over 2g, and then times the v partial derivative of that's going to be xvv, but xvv is this, and then the term I get that I'm collecting is gv over 2g. Okay? And then plus I get the derivative of L times U, which will go over here, plus L times the derivative of U in the V direction, and then that has a V term which is minus N over G. And there you go. We've computed all the terms that show up there. I'm not writing down the terms that show up there or there. Okay? And then you do the same thing down here, XUVU. And if you do that, let me just, and this is the same kind of computation, all right? And you get a minus E V over 2 E E V over 2G, and then plus GU over 2G U plus GU over 2G GU over 2G, and then minus M squared over G. Now the point is that these two things are equal. That's our new identity. And then you stare at that for a little bit. You say, wait a second. If these things are equal, isn't this? If I collect these terms right here, I'll put this to the other side. I'm getting Ln minus m squared over g. Wait a second. Isn't k Ln minus m squared over eg? Remember, f is 0, right? And you're like, it is. Wait a second. If I just divide through by e on both sides, and when I collect these terms together, I get an Ln minus m squared over eg, and that's k.
What happened?
This equals that. And so what you get then is that Ln, L times n, I'm putting this to the other side, right? So this equals that, right? This whole thing equals that whole thing. Let's come over to this side, right? You get an Ln minus m squared over g. Y'all see that? If I put this term to the other side, I collect these two terms, that's what I get, right? Okay, now divide through by e. And I get this. Okay? And then and then I want to get a bunch of other stuff. Okay, put the other stuff on the other side, okay? Bunch of other stuff, okay? These terms here, right over there, okay? Bunch of stuff, okay? And what is that stuff, by the way? Notice that it's not no L, M, and N's. It's just, this is just a function of E, F, and G, right? Well, F is 0, right? And then you stare at this for a second and say, wait a second, but isn't this just K? It is K. So K is a function of E, F, and G. And furthermore, if you collect all the terms and say where do you get, then we get this. I'll write it down again. Keep in mind, I don't even care what the function is. The main point is it's a function of E, F, and G, but it's minus 1 over 2 square root of EG. This is assuming that F is 0 times GdV of EV over the square root of EG, I think, plus EDU, partial derivative in the u direction, of GU divided by the square root of EG, close parenthesis, oops, close bracket. And there you go. And that's what these terms end up being when you collect terms in the nicest possible way. You can see that there's, let's see here. There's exercise to show that this equals that bunch of stuff. That's just Prague rule and stuff like that, right? Quotient rule. Key point is it's some function of EF and G, okay? But wait a second, EF and G is something that's intrinsic geometry. It's something the ant can detect. And so what we see is that this K is something that's is intrinsic geometry. The formula itself is cool and interesting, and every once in a while you need it to compute things or whatever, right? But really it's kind of the fact that there is a formula is the big news.
I can see how an ant would like evaluate. some
What's
of those-
that?
I can see how an ant would like evaluate EF and G, but how would it calculate like a partial with respect to phi? I mean, obviously.
Same way we do.
It's an ant. I mean, yeah.
I mean, the point is, it's like imagine you got latitude and longitude. Things are functions of latitude and longitude, and it's just at some point it's just a function of u and v. You just take a partial derivative, right? Express. In fact, you guys can do this. I mean, you guys have already computed E, F, and G, and they're functions of u and v, right? It's exactly just this is multivariable calculus right here. And so that's, in some sense, what the trick is we're turning everything into multivariable calculus, right? You're using linear algebra and our understanding of three-dimensional geometry to turn understanding the geometry of a curved surface into doing calculus in the UV plane. Isn't that cool? I mean, ultimately, we're computing K, the curvature of this thing over here, the intrinsic curvature. And in fact, we're even computing the shape operator, and all the curvature quantities over here are being computed really just as functions of u and v in our coordinate chart. Because we understand multivariable calculus so much better, right? Like that's something we know and we can do, and that's just on the flat UV plane. And then we just compute these things, and oh, by the way, this function K of u and v is the Gauss curvature over there at the corresponding point. Does that make sense? I mean, that's the remarkable aspect of all this. That's sort of the breakthrough idea. And that's what Gauss called his remarkable theorem. And and Gauss was hard to impress, too. So the fact that this was what he liked this. He was like, remarkable. There's something called intrinsic geometry. Before that, I mean, it's like, okay, we could talk about the ant and the fact that I can convince you that there is an experiment the ant could do to detect that intrinsic geometry. But now we have a formula for it. And it's like, oh, okay, this is intrinsic geometry. And then Gauss had a student named Riemann, who apparently was also a genius. I mean, it's like a high density of smart people, or was it that Gauss was a good mentor? I don't know, because all his other students weren't geniuses. So, and Riemann pushed these ideas further and to define the idea of higher dimensional manifolds. Like Gauss was mostly sticking around to 2 dimensions, and Gauss realized hyperbolic space existed, even though you can't embed it into R3. But then Riemann has said, okay, what about n-dimensional spaces? And Riemann died when he was 40, by the way. Man, I'm always impressed by these people who do so much and they're like dead by the time they're 40. Like I'm 53. It's just kind of like, wow. And of course, Riemann did, and Gauss did too. They both, did a lot of things. Both did number theory quite notably. Of course, I don't even want to list all the different things that Gauss did because I know I forget something. But statistics, the Gaussian normal distribution. So it's both pure and applied in retrospect. But then Gauss and Riemann missed something. When Riemann generalized this notion of EF and G and whatever, what they both realized, especially Riemann, was that, you know what? Now let's get rid of the 3-dimensional space. let's define a metric just to be any E, F, and G. It's just like, don't compute E, F, and G, just start with an E, F, and G. Take a coordinate chart and just pretend like you got your E, F, Gs from embedding into R3, but don't actually embed into R3. Just let E, F, and G be anything you want. And then do all these formulas and compute all these things, right? And that was the beginning of Riemannian geometry. And that's what we do when we're doing general relativity, essentially. It's just like, let's do everything we're doing here, but leave out the R3 thing. Right? Because this formula for Gauss curvature still makes sense. It doesn't matter. Does it matter if the E, F, and G came from an R3 mapping? In other words, you don't need an S. You don't need this picture over here. Just start over here and just define E, F, and G be whatever you want. And then there you go. There's your Gauss curvature for any functions of E, F, and G you want. And the only thing they missed is that they require that E, F, and G, when you make a matrix out of it, they wanted all dot products to be positive. They wanted you should only choose E, F, and G so that a vector dot product itself was always going to give you something either 0 or positive. Because that's something you get in R3, right? Any vector dot product itself, right, is always going to be this length squared, right? So you think that any vector dot product itself should have to be either 0 or positive, but couldn't be negative, right? Well, so Riemannian geometry assumes that any vector dot product itself, when you use the E, F, and Gs, that it has to be non-negative. And when you get rid of that assumption, that's called Lorentzian geometry, and that's the geometry of special relativity, and then ultimately general relativity. And so that's the crazy thing, is that that's just an artifact of, we think of surfaces as being in R3, but if you truly get rid of R3, there's no reason why a vector dot product itself has to be positive. And that's really, they kind of miss that. Like, we think of mathematicians as being abstract and just doing all kinds of crazy stuff because the formulas make sense, so why not, right? And this isn't a case where the mathematicians kind of missed it. They were too applied. They were too influenced by the picture in R3. They couldn't say, well, this would be nonsense, right, to have a vector dot product itself. They were still thinking like, oh, wait, maybe these things embed into some Euclidean space. I just don't know what the embedding is, right? And so that they didn't get through that, which is, it's interesting to observe in retrospect, right? Because like we celebrate these geniuses, but at the end of the day, they're human beings just like us, and in fact, they're not. The danger of using the term genius is that you might think that you're not a genius. You could be a genius too. Do some great work and then get a good PR department. No, I mean, it's, why not, right? It's just a term. And so that's what special and general relativity are. It's just dealing with the E, F, and Gs, and don't worry about the larger space. Right? What are the possible geometries that you can have independent of whether it can be embedded in a larger space? So we'll get to that eventually in this course, but our first glimpse of it is this formula right here. Gauss curvature. Okay, see you guys next time.